So basically, we have to have an ID document anytime someone does a money transaction. And currently, it's done manually. And it takes a lot of time because people constantly forget it. And when they do bring it, it's kind of, you have to type it in on your phone. And it has numbers and dashes and all that kind of stuff. So it adds a lot of time to the transactional part. And our idea is to try to get the transaction time down as quick as possible so it's less pain point for our consumers. And there's also mistakes that happen, and it becomes really tricky to identify consumers because if you use one identity number but they make a mistake on it, then we have a new person in our database. So what we want to do is basically automate our OCR using some kind of app. So we just released a new kind of app for our tellers. And so it allows them to do transactions on a smartphone, which should make everything easier. And so the end-to-end system idea that we had when we were designing this thing is that the teller would take a picture of the ID, and then this would send it to a cloud storage thing in the ether. And then they would request our OCR API, which is the thing I'm building. And that thing would kind of process it and say, all right, I need this image that you just took. Let's send it to some kind of black box neural network thing that does the OCR and gets the images, and it spits out an image, and then the OCR will send it back to the phone. And so our prototype is going to be this. Obviously, in the future, we'll have all this stuff happening on the mobile phone. So you take the picture, the OCR happens immediately. But when we are trying to gain the data for training, we want to store it somewhere. So we have that intermediate step. It also means that I don't have any constraints on how big my neural network can be, which is kind of nice. So when I started this project, we had very few ID pictures in our database. I think it was like 300. And so my sneaky idea to get around this was to try to train on some simulated images and then transfer learn when we get more data onto this other stuff. And of course, when you launch a new app, there's lots of bugs and stuff like that. So the image quality in the apps was just terrible. So I was really fighting with image processing on that. It also turned out data is really expensive and it's hard for people to use data. So people were skipping that step altogether because there's just too much effort. So even though we were getting lots of transactions on this thing, it was not very many people actually sending the images to us. So it was just a whole nest of problems that we were having in the beginning of this app. But now we've solved a lot of them. And another problem is that Zambian identities aren't standard. So when you have a driver's license or passports, there's kind of some kind of general legislation that most countries follow to make them, and then you can have another company do the OCR for you. So this is kind of what a Zambian identity looks like. So it's actually hand typed. So each person will go to a person, and they will type the identity number in on this piece of paper. And so they can make mistakes, and they push the backwards button, and it'll actually go and have two letters printed on each other. There's also weird orientations on them. And this is the front of the document, but there's no way to tell the front of the document and the back of the document are the same thing, because there's no identity here that would tie it to it. And then the back of the document, which I can't show, has all the person's personal details. And also there's lots of little small boxes, and the text is slightly too big, so they often bleed over and stuff like that. So it was going to be really difficult to try to get this. And then you got the picture of the person, some kind of signature, a thumbprint, which does whatever. And then also these kind of wavy lines that are supposed to be anti-tampering kind of things. So all the wavy lines really cause the OCR kind of off the shelf to not work very well because it's anti-tampering and stuff. So what I did is I started off with Tesseract, which is kind of an old school OCR that's been around for a really long time. And I just was like, all right, let's just throw this image into Tesseract and see what happens. So first you have to binaryize the images. So I just turned everything to zeros and ones. And then you stick it in Tesseract. And this is what Tesseract spits out for you. And usually it finds this part down here, the signature of the holder, because it's not on the anti-tampering side. Or this person had the signature halfway through it, so it could find most of this part. But it doesn't really, it really struggles with trying to get the text that I actually want out of there. So yeah, so that was kind of a problem. We couldn't just do that. So then I was thinking, maybe we can be a little bit smarter, and all we really care about is that text. Oh, sorry. So now if you rotate anything, because Tesseract is made for books, and reading text out of books, so you always know the orientation of books. So as soon as you rotate this, and I rotate this by 5 degrees, it's unable to find anything. So obviously, when we have people in the field taking pictures, they're going to have different rotations. There's going to be bright lights in the background. You know, they might actually take a picture of their finger in the image. So Tesseract didn't seem like it'd be robust enough for us to have a thing on. And so then I had an idea using like the Google Translate app is like maybe we can have them take the picture and then just select on their phone like the part of the thing they want to do OCR on. And we'll kind of constrain the amount of processing we need to do on our side down to a small thing. So now you just get a little text box when you do that swiping, and it selects it out, and then I rip it out. But Tesseract still kind of has a hard time identifying anything. And even in this kind of binary situation, it's a bit difficult to see the numbers there. So yeah, I started off. So like I said, we only had a few images in the beginning. So my great idea was to do the transfer learning. So I had to kind of simulate my own NRCs. So I spent weeks literally trying to draw out those wavy lines and printing stuff on there to get simulated images. And so this is an example of one of my simulated images. So it looks pretty good, and I got rotation in there and some kind of other effects and stuff like that. And the only thing I really had problems with was getting the fonts right. And we can talk about how to get fonts out of Linux. It's really difficult. And so even in Tesseract with my simulated images, which I can produce millions of these things, it had a hard time with it. So I kind of starting off with like a really simple model for OCR. So we all kind of know about character classification. So we got MNIST, and you can get up to like 99% accuracy on MNIST. And like be able to classify these characters. And there's other data sets of characters like 74K things where you can go and just classify tons of characters and you'll get really good accuracy. So I was thinking maybe I can just bolt that on and see if I can come up with an algorithm to extract images and do that really easily. So I start off with MNIST, and to make it a little bit more robust so it looked a little bit more like my images, I added some noise to the images. I added a null class because obviously you don't want it to always predict a number. You want it to predict that there's not something in there. I was going to do rotation, but I didn't get around to it, and off-center stuff, and I didn't get around to that either. But this is kind of what it looks like when I do my processing. So now you have a blank class, you have some numbers with lots of noise in there, and yeah, so it looks difficult. And this is the kind of network architecture that I found in the Keras examples place, where they just have CNN, so convolutional neural network, that goes to a fully connected network, and it kind of spits out the classes, and it takes a couple seconds or a couple minutes to run. So I ran it, and I kind of commented it out when I was doing this talk, but basically I was getting 98% accuracy on recovering the correct characters when I did that really quickly. So it looks like everything was going to be straightforward. But now the problem is actually coming up with the algorithm to extract boxes out so that it can run character classification on the different parts. So yeah, this is an example of it classifying things. So it found a 3, it found this one as blank, this one's also blank, and it found this one as a 0. So it does a pretty good job. Sometimes I would even have to squint and see if they're actually a real image. Yeah, so what I did was a kind of sliding window approach, and it's just kind of very straightforward. So each one of these green boxes, I would extract that, run it through the classification, and see if it would come up with anything. And the next part would also try to deal with the scale invariance. So if the image is further away or closer, so you need to be able to have a way to deal with that. But I didn't implement that in this talk. So basically, I did that, and I came up with all these boxes, and I stitched them back together after I was done. And I was hoping that it would come up with some kind of red haze that said that it found a character. So when I ran it through this example, it actually didn't find any characters at all. So each one of those pink boxes is a box, and black meant that there was no characters found in there. And if it was red, that meant there should have been a character in there. So I didn't find anything. And so it wasn't very nice. And doing all that kind of invariant stuff was really tricky. And also you might notice that like a lot of these boxes kind of take half letters in them. And so you need a way to be able to deal with that. And also there's like this dash in there. And all the character databases I found don't have dashes in them. So I'd have to create my own character database of dashes. And so it just became really algorithmic and like a lot of processing. And neural networks are supposed to be easy. So yeah, you have misalignment of numbers because the boxes are just kind of randomly moving across. You have to deal with spaces. So sometimes they'll put a space in the character. So how would it deal with that? Would it just assume that it's a blank or something? The images are different size, and like I said, the noise will be different for every image. And I just wanted a more robust kind of OCR program than what I could do with that kind of thing. So while I was reading up on this stuff, I found this loss function, which is called Connectedness Temporal Classification, or CTC. And it's a nice function where you can have some kind of output, and you don't really care about the alignment of where the characters are in this output. It has an algorithm to be able to figure it out for you. So it's kind of a black box of loss functions that makes life really nice. And the other thing is that they work really well with RNNs. So usually they use them in speech and audio recognition and stuff like that. So you have some kind of waveform, and then you're sliding a window through it, and it'll tell you where the phoneme is. So this is the same thing. So now we'll just apply it on a ID document instead of something else. And basically what you're doing in this thing is you're trying to maximize or minimize, if you take the log, some kind of alignment of valid paths in this thing. And I'll talk a little bit more about that in a bit. But that's basically the objective function that you're doing. And it's got nice properties that it's differentiable and all kind of stuff like that. So basically what I want to do with this network is stick in an image, have it go into my black box network, and spit out an output. And then I would have some kind of probability of different classes coming up. And so with the CTC, you get this kind of repeated characters and all sorts of stuff like that. And so all you really care about is if there's a repeated character, you're just going to merge them together. And just anytime something changes, that means there's a new character coming along. And since, like we had with the moving boxes, you can have like half a box will have half a number and the other box will have the other half. So this thing is able to deal with that because it just will predict a duplicate character afterwards. Obviously, it works really well for cat, but now if you want to say look for a word like hello, where you have two L's, you need a way to tell between the different L's. So you have to always add an extra class to your classification now, and you just have this kind of EDA symbol, which we use in this thing, which is like a split. And so it can be used as a space, or you can just use it to split your words up. And in the end, you get your output, and you get your probability of classes over some kind of time period. And now you're trying to find valid alignments. So how does a valid alignment look? So it's something that's just changing monotonically. So every kind of pixel on the time axis, something will change, and it can stay the same, which is fine. But as long as it's not you're not going backwards on this image, life is good. And then you can have these things. So like an optimal path here would be starting off with this H, and so the darker the color, the higher the probability. And then you'd move over to the E, and then after the E, it looks like this null character is a bit better. And then you'd have a double set of L's, and then you can also go down here to the blank, and that split up the L's now, and then you got the O's at the end. And you can have these blank characters kind of anywhere, so we'd have hello here, and then you'd kind of combine them more. Another optimal path, or a good path too, you could start off with the blank character, and then kind of move up to the E's, and kind of follow the L's, and back down, and then get the O's, so then you'll get something like helio. And so with that last equation I had, you'd take all these paths these valid paths that you got, you'd sum up all the probabilities of them, and then you're just trying to maximize that all the possible kind of combinations of valid alignments are coming out correctly. So that's basically what you're doing. Don't ask me how you'd implement it. That's a little bit more difficult. So this is kind of how your CTC network would look like. Maybe I can zoom out a little bit. There we go. So you got your image space, which is kind of like a RNN pixel now. So it's a weird combination of pixels over some kind of structure in your image. And then you have your different classes. So I got 0, 1, 2, 3. And then I can add the dash class because I don't need to worry about anything special about it. And then I have my null class up here. So then I can look for the optimal path, and obviously this is not a very well-trained network, but you can start up here and then maybe move down here for a bit, then move back up here when you go to the newer probability, and then kind of finish off at 1 or something like that. So yeah, that's kind of how it looks. Yeah?
What's the color coding?
It's just probabilities. So higher probabilities are yellow, black are low probabilities, and you can see the scale is quite small. So it's not very sure about these things. So yeah, valid alignments are very important when it comes to this. So I just want to reiterate that they just got to be like changing. You can't go backwards to get another one. You always got to move forward on the time space. So you are assuming some kind of continuous structure as you go along. And then you merge them and you get your blanks, and then you get your final word at the end. So a nice algorithm. So now you have the CTC. Now you want to decode it and get your word out or character that you're getting. So you need a way to decode that CTC. And we'll use the concept of valid alignments. But obviously, there's multiple paths that you can have. And also, different alignments can actually give you the same word. So if you have all these different alignments that are adding up to be higher probability than your max best likelihood path, you might want to change the order of those things. And you want to be able to have an algorithm that can search through the space and figure all these things out. So a nice one to use is beam search, because this gives you a kind of trade-off between computational and the number of searches you do. It's not a kind of thorough search. It will just allow you to have that trade-off. And so basically what you're trying to maximize is like you have your character given some CTC output, and you're trying to find the max path that gives you that. And yeah, I said all that stuff. So what's an example of beam search actually working? Let me reset the size. There we go. So you basically have two options when you do a beam search. You have the number of beams and then the number of end solutions you want to get out. So in this case, I do a beam search with 3 beams. So then at the beginning, I have 3 different starts of this. And our search space is only over the null character A and B. And so we start off there, where we choose one of these 3 options. So we can start with this top one. So this guy chooses a null one, and it'll move over to the next part. And so you're kind of building up a tree of possibilities as you go along. So it didn't select anything, so now it's able to find the next kind of likely character, which in this case turns out to be an A since it's red. And then it moves on to the next one, so it gets another A, or that's the hypothesis. So now it has an option of two characters that have high likelihoods, but they actually collapse to the same thing, because you got a blank character and another A, which would collapse into an A anyways. So you get that one beam. Second beam kind of goes down here, and you first start off with an A, and then you have an equal probability to select all 3 of these. So now the beam can follow this path up here and kind of use the other one's computation to help get the finish of it. It can also go down here with the B's, and now you get an A-B combination at the end. But it doesn't seem like it's very probable that it was that one. And the third one starts off the B, and then you figure out the next one's an A, and it'll collapse it down for you. So that's kind of how it works with 3. You can obviously do as many as you have memory for, which is the trade-off. And if you're talking about figuring out word embeddings, you'll have character classes of thousands of words or hundreds of thousands of words. So obviously you don't want to have tons of beams. You'll run out of memory. But in my case, I only had 11 characters, so I could almost just do every possible search in this thing. But luckily, beam search was already kind of implemented, so I didn't need to worry about it. Okay. So now that I know about CTC and beam search and stuff, how would I build a network to do this stuff? So I find when you're doing machine learning, the best way to do things is just ensembles and stick things together if they work. If one thing works and another thing kind of works, put them together and you usually get something that works a lot better. So basically what I did is I took the kind of infrastructure from the MNIST classification and I just bolted on a bidirectional RNN. So that allows me to have structure in both directions of the image, just in case letters have different ways of being shown. And then I just have the CTC output at the end. So it's just kind of bolting on more things onto it. And doing CNNs is pretty cheap, so it's not a huge expense. Most of the computational time is stuck in those bidirectional neural networks. And I built all this stuff in Keras. At my job, I don't really have too much time to really fiddle with stuff. So building things as easy and quickly as possible seems to be the best way to go about it. So that's what I like about Keras is you can just kind of bolt everything on. I don't really need to deal with the nitty-gritty of TensorFlow and declaring variables and doing all sorts of stuff. And also if I do, like I can always, the nice thing about Keras is it uses TensorFlow in the back end, so you can do all the nitty-gritty stuff if you want. So a lot of the time I spent was kind of figuring out the kind of actual nuts and bolts of the network. And it was kind of solid research. So you'd have a hypothesis, and then you'd go run a model on it, and you'd get an answer back. And then you're basically just prototyping and checking these things out. So things that helped me a lot were reading papers and talking to people, because you only have so many ideas in your head at one time, and then you forget them. So it's good to talk to people and remind you about those things, or they'll give you new ideas. So I also like scaled down my networks. So instead of having like the most beefy network possible that would do all the things, I'd have a network that probably couldn't actually work on this data set, but it gave me the chance to kind of see where things are improving really quickly. So I could run through a network in like an hour instead of weeks. And so that really helped me kind of prototyping and doing stuff like that. The smallest network I'd have is something that could memorize a really small subset of data. So I'd stick in like 10 examples, and it would have to give me 100% accuracy on the output of those 10. And so all it did was just overfit on the network on those data sets, and was able to do that. So once you have a network that you know can at least do the minimum problem, then you know you're at least on an architecture that can work for you in the future. And also, like, I set up a lot of quick benchmarks for myself. So my benchmark was like after 10 epochs, I would get the loss function for that, and then I'd use that to like benchmark my hypothesis and stuff. That actually bit me in the ass later because it turned out the low number statistics basically. And a lot of stuff just doesn't work. And so it's like research. You know, you start off and you have a great idea, and then you start working on it and you realize it's a terrible idea and you're terrible. And then eventually you get to a point where you realize, that's why, and you feel great, and the problem's great and you're great. And so you kind of go through that cycle a lot. And that's the problem with deep learning. It's still an art. You know, a lot of people talk about how you tune things, and most of the experts just have that intuition. So without intuition, you just got to go through the bowels of it. So this ended up being what my network was. So I had kind of stacks of convolutional neural networks, and then a max pooling, more neural networks, then pooling, and then I had like a dense network, which this thing would not work without for some reason, that then bolted on to my bidirectional stack, and then that stuck on the CTC output at the end, which is below the image. And in all, it was only 5 million parameters, so it wasn't too many, but that's still a ton compared to what you do in machine learning. And a lot of the hardship I had was not using batch normalization. So my stuff would constantly just blow up. I'd have exploding gradients or shrinking gradients, or things would just go null for no reason. And as soon as I started playing around with batch normalization, like, it just made my network really stable. So I'd say start out there with like good batch normalization everywhere, and then figure out where you can remove it from at the end. And the other thing I kind of was playing around with is trying to see what the different convolutions were learning. And so my images all had like boxes in them where the ID box was, and then some kind of text. So I try to visualize some of these layers, and what really comes out of some of these layers is mostly noise. It doesn't look like very much, but some of them you can kind of see that it's looking for boxes in the images. So it's finding convolutions. And then this just looks like a kind of edge detection or water or something in there. And then this one almost looks like a kind of blurred together group of numbers on a box. So it is learning stuff in there, but trying to explain it to other people is very hard. And this didn't really help me very much. Besides it's learning the box, I don't really know else what it's doing in there. So now it's time for the final part. So this is me running it over the last night because for some reason my model got deleted between when I first created this and yesterday. So I was trying to run this thing, and I ran it all night, and this morning I've been running for 18 hours, and I was like, all right, it's got a great loss function. Let's see what results it gives me. So off this image, which starts with the 7, which is kind of nice, it just gives me repeating 7s and 2s. So that's not great. It's always nice to have good results when you give a talk. That's lesson number 1. And I was thinking like, oh, maybe you figure out this 7 and this 2. So I put a real NRC in there, and C would spit out the same thing. So I think it's just there's no it's not gaining any insight. It's just kind of a random output that it's putting out. And I guess that's what I get for trying to do this stuff last minute. And this is kind of more what the real images look like. So it's very hard to see, and there's aspect ratio issues, which I never took into account either. Yeah. So some other things like general purpose, like hygiene things for your prototyping. So when you have notebooks, like they're great for prototyping. But a lot of times, like you'll delete something or change something, or you don't version them properly, and it causes a lot of problems and heartache because you have to go back and reproduce it. So I try to keep all my models separate from my notebooks. So I'll just kind of create it, comment it, put unit tests on it, and then store it on Git. And then I just import those models into my notebooks instead of trying to write them in the notebooks. And that seemed to really help with doing it because you can forget what you did in a notebook, but at least the models are actually hard-coded and ready to go. The CTC loss function, I had no idea what it actually meant. It would just go down to 0, and I thought that was like it'd be its maximum, but then start going negative, which I have no idea what it meant, but it was probably good. So in the end, I would get down to 0, and I was like, all right, it's done. And then I'd kind of run an output on there, and it'd give me gibberish. So like having like a good metric that you can kind of, something that you understand that is actually explainable to yourself and other people is much better than just having a metric that optimizes stuff. So in the end, I try to use edit distance to try to figure out these things. But edit distance doesn't has kind of constraints when it comes to lengths of characters. So that was a problem. Yeah, and like I said before, if something's going on with it, try batch normalization. That fixed all my problems. So in the future, like since I ran this, like neural network has gone through regime changes and paradigm shifts. So now everybody's talking about text segmentation or segmentation and stuff like that. So you can actually build a classifier that will get your bounding box around your text and just extract that out and then run it through an OCR. So you don't have to worry about noise or anything like that. And that's supposed to work really well. I haven't actually tried it yet. And then there's all these like data sets of text box, figuring out where text boxes are. So it's called text in the wild. And so I'd like to try something like that. Obviously, I don't think it would work very well because, you know, we have a very kind of one type of use case where they're just putting boxes on beaches and people surfing and stuff like that. So it may not be the same kind of distribution as what we have in our data. And last but not least, I also run a deep learning talk series or machine learning talk series. So it's coming on at the end of the month, last Tuesday of the month. So definitely come check it out. It's good if you like talking about kind of nerdy things like this stuff. You can get your nerd on at least once a month. And there's our website. We're just Machine Learning Cape Town. And there's also Deep Learning Cape Town. And we're basically the same thing. So you can come check us out. So cool. Thank you. Yeah, questions?
Do you always binarize the image before you pass it to a classifier?
I started doing that for this talk because it seemed like it would simplify the kind of pre-processing I would have to do. But I think it caused my network to not converge as fast as possible. So, but it...
Yeah, also because the background is fairly predictable, so I guess if I had to do it, I would try other way.
Yeah, so that's the other thing. So the new system that they're building to save data is they're going to make all the images black and white. So I'll only have color when I scrape it off the internet. The normal ones will just be black and white in the production ones. So yeah, I wish. Yeah, you had a question back there? Yeah, okay.
So you mentioned when you were trying to find like optimal parameters of the network or whatever, you went down to a smaller network and then find like on the small data set you have, it could overfit, and then you would do almost like selecting the best model you could find on that. But is that, I guess your hypothesis is then is that the parameters that you do find will also be the ones that would work once you scale the network up?
Yeah, exactly. So I assumed, which may not be a good assumption, that the architecture is the most important part of it. And once you get a good architecture, like all you need to do to make it robust is add more parameters to it. So from that sense, like, yeah, you can have a small network. It works well. You can benchmark it. You can see if it's converging faster, or you're getting better numbers, or if you need more regularization, you can put that in there really quickly and still keep it robust. But then when I actually did scale it up, I found that it wasn't completely accurate. I ended up with 3 models that performed differently on my small data set, but they performed exactly the same when I scaled all of them up. But that's...
So like learning rate, for example, if you tried like a grid search of learning rate with a smaller model, then you would find the best learning rate you could find, but then just use that with the bigger model.
Yeah, exactly. And actually, like, one of the main problems I had was I was using Atom as the optimizer, and it worked great for the small models. But as soon as I scaled it up, it stopped working completely. Like, my network wouldn't converge at all. And I actually ended up going back to stochastic gradient descent because that converged for some reason. And I have no idea why that worked. I just was trying stuff, and it started converging after a while. So, yeah, you had a question?
I've seen a similar network where you combine a CNN very good network for image captioning. So do you actually have, in that case, the two can actually communicate, so the RNN can backpropagate the gradient, right? Because it's just a vector to the CNN.
Yeah.
Do you kind of have that as well in your case, where any sequencing errors are passed back to the component, and then the component can kind of wiggle the weights to sort of adjust in order to head towards like better sequencing in the RNN.
Right. So the reason why I started off with that was I was thinking transfer learning. So there's all these like really nice convolutional neural networks that I could just transfer learn onto my network and then just stick it on an RNN and do the rest. But it turned out like the RNNs were most of the features actually most of the work was actually being done. I can show you really quickly. So we had these convolutions where you have like maybe tens of thousands of parameters in there, but as soon as you get to the bidirectional things, you're in almost millions. So like it didn't really matter what this was, as long as I had this time dense, whatever this kind of structure was, gave me basically the same results. But this was mostly so I could get some kind of spatial structure, because I knew it was going to be doing a sliding window kind of stuff in there. So being able to have some kind of sliding window structure, so you don't really care about how big the pixel is or the distance from the image that you're taking a picture of. It would be able to deal with that invariance through the RNN going back and forth a couple times. So yeah. Yeah, at the back.
Two questions. Question number one, would you maybe make this talk or this slide available somewhere?
Oh yeah, it's on my GitHub. So
Would you maybe share the link?
yeah, Dr. Danger, Simon.gmail.github.io.
And second question, I was interested when you were showing about the bounding box approach, using tesseract. I was wondering, did you ever think about like background subtraction and then a grid search over like different bounding box shapes? It seems like you might be missing out by like too much or
Yeah. So I had a slide where I was going to do this pyramid shrinking. So you start off with like blowing up the image, and then you shrink it down like by factors of 2 or something like that, so that you're able to get every kind of scale possible. And you just come back with the most likely characters from that. But I couldn't get the image, the box window sliding thing to actually show up properly. Yeah. And then the other idea was that we're going to do lots of post-processing, so like classic image processing techniques. So do edge detection and word segmentation, Sobel filters, all this kind of stuff to try to do it. But when I was training these images, like I had millions of images that I could generate, and then I'd have to do all this post-processing on it. And it actually became computationally intractable to build these images, then do the training or pre-processing, and then stick them into a training thing. So I just kind of gave up on that and just decided to binaryize them. Cool. Awesome. And I think that's all.